Okay. Yeah.
And it could be for the
That works.
final exam or whatever too. So, but I just want to go through and make sure that, so before you take the test, that you kind of know what my expectations are, what I'm looking for, and stuff like that, so that we can make sure you're squared away. Because Amber said you're meeting at 5. Oh, you muted yourself now.
Yeah. Yep. At 5.
Okay, perfect. So anyway, so the stuff that you completely understand, great. We can just buzz through it. But then I want to make sure that my key versus your keys. So I think I can share a screen, and then I can write on this too. So like I could actually, if you want me to get in and work something out step by step, I can do it. I should be able to do it anyway. That's the theory.
Perfect. Okay.
So do you see, hopefully you see section 2.1 homework?
Yeah. Yeah. I have it here in front of me too.
Okay, perfect. So anyway, and then I could share the key as well, but long story short, yeah, I mean, anytime you're graphing something, this is like, we could rewrite that as x minus 3 quantity squared, and then that's just a base graph shift. But anyway, I'm always going to want the x-intercept or intercepts and the y-intercept on that one. But then kind of what you did is you use the theorems, which is later in the chapter when you were taking derivatives.
Yeah.
Which, basically, in class, I wouldn't like it, but this, you're going to need to use the limit of the difference quotient at least once, because I'm going to tell you to use that formula on the test.
Okay.
So I want to make sure, do you know how to use this formula? Or do you want me to?
No. Yeah. Can we go through it?
Yeah. So like if we're doing, this one here, I guess you didn't give me the x-intercepts and the y-intercept. I mean, you gave me the relative max there, which is fine. But anyway, so I just wanted to make sure you're aware of that. So we could do, instead of just looking at the key, I can do like number 8, I think. So let me go back to my session, share the whiteboard. Every once in a while it freezes up on this. So
Okay.
you got your phone by you too, right? In case we have issues.
Yeah. Yep.
Okay. So can you see the whiteboard?
Yeah.
All right. Perfect. Oops. Switch to tablet mode. Wait a minute. Where'd my whiteboard go? Share whiteboard. You probably can't see it anymore, right? So I got to get my pen out. I didn't do that yet.
Oh, so I see the whiteboard now.
Yeah. When I flip, like I got to flip my computer so that I can write on it. It's been a while since I've done this, but let me just, I got my other computer open too. So let me, all right. So when we have this would be number 8. So you can see number 8 now.
Yeah.
Okay, perfect. So we have f of x equals 7 minus 6x minus x squared. And basically we want to find the slope of the tangent line, and we could do it either at a particular point or at any point x. So slope of the tangent line at any point x. This is just f prime at x, right? So it's f prime.
Yeah.
But it's the limit as delta x, the change in x goes to 0. You might have used like an h, limit as h goes to 0 or something like that in high school. This book uses delta x. But anyway, it's f of x plus delta x minus f of x all over delta x. And what this is this is just rise over run. And so, if we have our graph going like this, then this is the tangent line. And if you do, I'm going to change colors here maybe. So if we do right here, this is rise over run. This is the change in your height, delta y. This is the change in the x's, delta x, right? And so the slope of the tangent line at any point x here, so the slope of the tangent line is basically, well, this is the slope of the secant line. The blue one is the secant line. It connects 2 points on there. So this would be like the slope of the secant line would be delta y over delta x, right?
Yeah.
And so the change in the height, you know, when we have our graph here, this is the 2 points right here. So I'm over at, if this is x, and then I'm delta x to the right, this is x plus delta x. And so this is f of x, with, and get back. Every once in a while, like, it's not letting me write. I hate this stupid ass thing. Okay, it's letting me erase. Maybe it'll let me go back and write. Draw. Okay, can you see me writing again?
Yeah, I see the f of x.
This is x f of x, and then this height here, this is what you're plugging in. So this is f of x plus delta x. So if I want this delta y, the change in the y, that'd be the top height minus the bottom height, right?
Yeah.
So delta y right here is f of x plus delta x, which is this height, minus the lower height, which is f of x. So this is just delta y on top. Okay, so that's where that comes from. And then the bottom, delta x, you know, that's just the difference between the right endpoint and the left endpoint. If you take x plus delta x minus x, you just get delta x, right?
Yeah, correct.
So that's that distance in here. And so basically the slope of the secant line, which connects these 2 points, is just delta y over delta x, which is this part right here. F of x plus delta x minus f of x all over delta x. And then what we're going to do is, because we don't want, like we actually want the slope of the tangent line at x, so which would be right here, right? That'd be the slope of the tangent line that just sits against the curve. So what we're going to do is we're going to let this delta x get smaller and smaller and smaller, and we're going to have this secant line slope is going to get closer and closer and closer to the actual tangent line slope. So what we do is we let delta x go to 0. And really, I showed it from the right, but we're also doing it from the left. So delta x could be a tiny negative number. So anyway, let's see how this, so this is just definition. This is just the definition of a tangent line slope, which is just the, you just took the derivative, right? So you're like, well, I know the derivative is minus 6 minus 2x, right?
Yeah.
So I'm going to show you, so let me clear this somehow. I got to remember how to do it. Let's see. No. Okay. So anyway, so the slope of the tangent line, or f prime, come on, gotta get back where I can draw again. So the slope of the tangent line at x. So we got to figure out what f of x plus delta x is, because that's the first part of the top, right?
Yeah. Well, that, okay, so that's delta y though, correct?
No, delta y is this minus f of x, right?
Oh,
So
okay,
anyway,
the whole,
this is going to be,
okay.
yeah.
Gotcha now, okay.
So I was trying, yeah. So anyway, this is f of x plus delta x, which I'm going to do that in green. And then,
and then once you take that minus the f of x, that's delta y, or yeah, delta y.
yeah. And I'm going to use different colors for this. So we use f of x, which is given. and then this is going to be all over delta x, right? So I'm going to figure out what f of x plus delta x is first. Well, what was f of x? So we had f of x is, what did we say? 7 minus 6x minus x squared, right?
Yep.
So that's f of x. So everywhere there's an x, we're going to plug in x plus delta x. So we're going to plug this in everywhere there's an x to figure this part out. So it's going to be 7 minus 6 instead of x, it's going to be x plus delta x. And then minus, instead of x quantity squared, we're plugging in an x plus delta x. So it's x plus delta x quantity squared. And all I'm trying to do is figure this first part of the equation out. Okay? And then you're going to do algebra and figure this out. So this is 7 minus 6x minus 6 delta x. So delta x is a variable. So just think of it like a z. If that was a z, it'd be minus 6z, right?
Yeah. Okay.
So we're just distributing the minus 6 through there. And then here I'm squaring it out. So minus, and I'm going to use parentheses here. So this is first, outer, inner, last. Right? It's just x plus delta x times x plus delta x, which is x squared, and then plus 2 times that thing multiplied. So it's 2x delta x, and then plus delta x quantity squared. So you just FOIL it out, right?
Yeah.
You okay with that? Algebra?
Yeah. Yep.
Okay. And then, of course, we're going to add the opposite to get rid of the parentheses. So opposite of x, that's negative, and that's negative. And so then what we have is this is going to be, I better make sure so it's going to be 7 minus 6x minus 6 delta x minus x squared minus 2x delta x, and then minus delta x squared, right? And so this is the first part right here, right?
Yeah. Yep. Okay. I see that.
Got that? Now, I
Yep.
need to figure out, and then I got to subtract f of x. Well, what's f of x? F of x is right here, but it's 7 minus 6x minus x squared, right? And I'm subtracting that whole thing. Well, subtract means add the opposite, right? And that's the numerator. This is the numerator. So now I'm back in black. So I'm doing the numerator here. I'm going to subtract f of x, which is add the opposite of f of x. So what happens is the 7's cancel, the 6x's cancel, the x squareds cancel, and I'm left with minus 6 delta x minus 2x delta x minus delta x squared, right?
Yeah. Yep.
That's all I have left on top. And then it's all going to be over delta x. So what I'm going to do is I'm going to pull a delta x out of each term and factor it out. And this is on my key too, but I wanted to step through it together. So let me see if I can clear this and hopefully keep writing. So basically, so we're still doing f prime, right? Come on.
Yeah. I mean, ultimately, yeah.
Yeah, right. So you're doing it the easy way, but anyway, so we're looking at the limit as delta x approaches 0, and then on top, what did we have left? We had minus 6 delta x, and then minus 2x delta x, and then minus, whoa, get back, and then minus delta x squared, right? And this is all over delta x. So basically, I want to, if you plug in 0 for delta x, we want to get rid of it'd be 0 over 0. So we don't want that. So we want to factor out the delta x. So it's the limit as delta x approaches 0. So the delta x, if I factor it out, I'm left with minus 6 minus 2x minus delta x, right? Pull it out by multiplication or distributive law, all over delta x. And then since delta x gets close to 0 but never equals 0, the same number divided by the same number, those cancel out to ones, right?
Yep.
So now I can go ahead and let delta x equal 0 because I'm not dividing by 0 now. So let delta x go to 0 or equal 0. And then, so what happens is that goes away and we're left with minus 6 minus 2x, which is f prime at x, right? But it's also the slope of the tangent line at any point x. So this is how you do it with the definition of a derivative. So if I say use the definition, which I can, before we get on, I can make sure that I've got it specifically that way. But if I say use the definition of derivative, I'm talking about the limit of the difference quotient.
This process.
This process, yes. And that's why I put on your, and you could tell what was red when I emailed. So like you're gonna have to do that at least once on the test.
Yeah, okay. Yeah,
So
well, that was going to be one of the things that I was going to have you, or questioned, that like, just to go over it, just to make sure that that's what I got it all figured out.
Just, you bet. Seeing me do it, or just seeing my answer key may or may not be, you may not be following it, especially on number 12, because that's an awkward one. I mean, we could do, whoops. What did I do? I quit sharing my screen. All right. But does that make sense anyway?
Yeah, no, yeah, that clears it up.
Okay. Do you want me to do one more like it?
Yeah, why not?
Okay.
Okay.
Let's just look at, I gotta get where I can write. Let's say we've got f of x equals x cubed minus 2. Okay. So f prime at x is the same as the slope of the tangent line at any point x, right? But by definition, so this is the definition of derivative, it's the limit as delta x goes to 0 of the difference quotient, which is f of x plus delta x minus f of x all over delta x. Okay, so this is the formula you need to know there. Stop it. Drawing.
Gotcha.
Anyway, so in this case, here's f of x. So we need to figure out each part. So f of x, I mean, that's this part right here, right? That goes directly in there, right?
Yeah. So
delta x is just some tiny number getting close to 0. So what I need to do, this is why I use different color, I need to figure that first part out. So what is, for this problem, what's f of x plus delta x? Well, I'm going to plug in f of x plus delta x everywhere there's an x. Well, in this case, it's only right there, right?
Yep.
So it's going to be x plus delta x quantity cubed, and then minus 2, right? But we need to simplify this out so we can get rid of stuff. So this is where I talked about Pascal's triangle and stuff like that in the videos. Did you watch the videos on that or not?
Yeah.
Otherwise, it would be, you square it out and then multiply everything else by x plus delta x and then use the distributive law twice. But this ends up being x cubed plus 3x squared delta x plus 3x delta x squared, which I don't need parentheses around the delta x, because delta x, like I said, it's like a z, so that'd be like z squared. So the delta is part of the variable here. And then plus delta x quantity cubed. And then, so that's the first part, and then minus 2. Good with that? So this is, so I just cube that out.
Yeah.
But you square it out, you get x squared plus 2x delta x plus delta x squared, and then you got to multiply it by the quantity x plus delta x again.
Yep, and then you just keep the -2 is just like tagged along there at the end.
It is, because that was here. So there's no x's there. Now, if that was minus 2x, then I would have to have -2 times the quantity x plus delta x.
Gotcha. Okay. Yeah. So that's I guess one of the things just to remember is like when you are doing like that first term, you just substitute x plus delta x into
Everywhere there's an
the
x,
whole thing.
yes.
Yep.
So
Okay.
for example, if I said, hey, what's f of 3? Well, what do? You plug a 3 in everywhere you see an x.
Yeah.
Well, it's 3 cubed minus 2, which is 27 minus 2 is 25, right?
Yeah.
And if that was a 2x, it'd be 3 cubed minus 2 times 3, right? But in this case,
Correct.
it's f of x plus delta x. So you plug that in for your variable. Everywhere there's an x, you're plugging in x plus delta x to get that first part. Okay?
Perfect.
All right. So then we're going to subtract. So minus f of x. Well, what was f of x? And this is a quantity, so it's x cubed minus 2, right?
Yeah.
This is in the numerator. And then all of that is going to be over delta. All of that is going to be over delta x, right?
Yep.
Anyway, so I'm going to add the opposite here. And what's really nice, when you got polynomials, some of this stuff cancels out. Come on. Okay? All good with that?
Yep.
And what am I left with on top? 3x squared delta x plus 3x delta x squared plus delta x cubed, right? And on the bottom,
Yep.
I've got delta x. And then I would take the limit. Limit as delta x goes to 0. I haven't done that yet. So that stays on until you take it at the end. But anyway, so now what I can do is I can take a delta x out of each one of these. Right?
Yep.
So let me rewrite it. I'm just going to make it look better for you. Just got to remember. Well, that's fine. So we had limit as delta x goes to 0, so I haven't done that yet. I had 3x squared delta x plus 3x delta x squared plus delta x cubed, right? Is what I had left on top, all over delta x. So I'm going to factor out a delta x so I can cancel it. So on top, so I haven't taken that limit yet, but on top I factor out a delta x, and I'm left with 3x squared plus 3x delta x plus delta x squared, because I took one out of each term and pulled it out front right here. So I factored out a delta x. Make sense?
Yep.
All over delta x. Now I can cancel these, right? Because it's not 0 over 0, because I only approach 0, I don't touch it. But now, what can I do? Now that I don't have a problem and I'm not going to have 0 divided by 0, I can let delta x equal 0, or go to 0, basically. And then if I do that, what happens? That'll go to 0, and this goes to 0, so I'm left with 3x squared. Right?
Yep.
Okay. Now, what was the original problem? The original problem was f of x equals x cubed minus 2, right? Well, what's the derivative of that?
3x squared.
3x squared, right? And you know how to do that real quick in your head, right?
Yeah.
Well, this is why. This is the proof. So this is the formal definition, but then in section 2.4, we came up with all these theorems and proven facts to do shortcut ways. So ultimately, when you leave my course for the summer and go on to grad school and everything else, I care that you can do this blue part, right? But this is the theory that backed it up, and it is, like I said, I'm just letting you know, it's on your test, so you're going to miss like half of the points if you don't do it this way. So you should be able to do it the shortcut way to know what the answer is. But to get the points on the test, you got to do like what I finished up in purple there.
Okay.
For that one. Now, if I say use theorems are proven facts, that's like the blue part down here. That's just using the quotient rule, product rule, stuff like that.
Yeah.
So you don't have to do the purple, what I finished up in the purple here. You don't have to do that on the whole test, but there's just one of them that you will. Okay.
Perfect. Yeah. I'll make sure I get points for that instead of just a 0 on that one.
Right. Okay. And then let's move on. And then the rest of the stuff, hopefully we can go through a little quicker. Let's see. I got to share content. Chapter 2 homework. I guess this one. Okay. So we're here. And then, the same deal. So like number 36. So basically these homeworks were 15 points because you had a lot more work to show. But in this case on 36, you'd put an x plus delta x and then quantity squared and then minus the 2 times x plus delta x. And then you multiply all that stuff out and then still have the plus 1. And then you subtract f of x on top all over delta x on the bottom, get stuff to cancel out. So there's just a lot of work versus what you did, which is actually section 2.4. And I apologize for not catching that before. The other thing that just for you to be careful of, this line does not equal this line. So you could say like f prime at x equals 6x minus 2. And I know that's what you mean, but that's not what I see here, right?
Yeah.
And so there's a couple other times that I tried to show that.
Yeah, I saw the one comment that it doesn't equal that, but yeah, I guess you still probably knew what I meant, but it doesn't actually equal that.
Right. So either the slope of the tangent line equals this or f prime at x equals this, either one. It means the same thing. So derivative for a curve at a point is the slope of the tangent line at that point. It's also the instantaneous rate of change of a curve at a point, which is measured by the slope of the tangent line. Here, I'm not sure, like I didn't see enough work. So like, I don't know if you went back to see, but you take the derivative, you get 6x. And then what number is that? 46. So the derivative is 6x, which is correct. And you want to be, but you got to be, like I think on this, if you look at my key, which you have this in front of you.
Yeah.
Okay, so let me go to my key because I've got that pulled up too. I think. Oh, I got to stop sharing that. Share the application or screen. Where's? Yep. Okay. You see the key now?
Yeah.
Okay. So anyway, so this was the line. You found the slope of the tangent line. You're trying to find the equation of the tangent line, but it's parallel to this. So the slope of the tangent line for this, you found by taking the derivative, but notice I did it using the difference quotient because I was in that section. Okay, so just for the one that you got to do this, you'll do it this way. You can also say, well, derivative 6x, do I match? And by the way, don't spend an hour of you and Amber's time if you don't get it to match. Just put, hey, I can't figure out why, but it should be 6x. Okay.
Okay.
Anyway, but then you get here, so 3x plus y equals 4. So the slope, if you saw that for y is the easiest way to read this slope. So the slope is -3 because I want to be parallel to it. If I wanted to be perpendicular to this line, I would need the negative reciprocal, and I'd be looking for a slope of positive 1/3, okay? But this is the slope of the tangent line at any point, and it needs to equal this. So we just set them equal to each other, and you find out that x equals minus 1/2. And when you find out that x equals minus 1/2, we can plug that into your equation to get what y is, and y would be negative 13/4. So you have the slope and you have a point. So I just use the point slope form, y minus y1 equals slope times x minus x1. But if you wanted to multiply this out, the answer in the back of the book, if this was an odd, would have multiplied this out and got everything on one side and got like y equals minus 3x plus whatever. 19/4 is what it should have been. Or
Okay.
minus 19/4.
Yeah, I see that there.
Okay, but anyway, so I'm not sure, like, so when I'm grading your stuff, like, I have no idea where you got the +6. It was, or -6, yeah, minus. I don't know where you got that. But do you see why, you know, we have different values here?
Yeah.
Okay.
Yeah,
So
that makes sense.
there'll probably be one like this on there. So you're using the derivative to figure out what the slope of the tangent line is. And then if you want to be parallel to it, it's equal. If you want to be perpendicular to it, you just take the negative reciprocal slope and then set that equal to the slope of the tangent line, right?
Correct.
Figure out the x, plug it back into your original equation to figure out y, and then come up with the equation of that line. If you'd rather use y equals mx plus b, that's fine. You're just going to end up figuring this point in, plugging it in, and solving for b, and then you get the negative 19/4. Okay, stop sharing. Whoops. I have no idea what that is. All right, stop sharing. All right, well, this is working better. Every other time I've used this, I've had technical difficulties so far, but let's just go back. And I'm not going to take this much time on all your homework, but like the first ones were, you know, there's just more stuff there.
Yeah.
Here on this one, like, I don't know, I think these were ordered pairs and you're trying to tell me the output or something like that. But then, like, I mean, these things were off here.
Yeah, I think I forgot the 2. I think I forgot to double the 2. Maybe. I don't know.
Okay. Yeah, and that's something where I'm looking at my. So we got right and left-handed derivatives there. And so when you're using the difference quotient, it's just approaching from one side. Like the left-handed derivative approaches, delta x approaches 0 from the left. And the right-handed derivative, delta x approaches 0 from the right. So in this case, you got to know which one you're on, right? If I'm approaching -1 from the left, I'm on this curve. That derivative is 2x plus 1 to the first times the derivative of what's inside, which is 1. So it's just 2x. And then you can plug in -1, get -2 for left-handed derivative slope, which I'm not sure if that's what number is that? I think I'm looking at 1. That's 22. I think on this one, like, it's trying to make it a continuous graph, or what was this? Is that what it was doing?
On 22?
Yeah.
I think so.
So you're trying to come up with this, like the equation of this line, right? Well, you know it's a line, so it's y equals mx plus b, but then you got to do rise over run. The rise is 2 and the run is 1, so there's your slope.
2.
And then the
Okay.
y-intercept is 2, so y equals mx plus b. So that was
Yeah.
part of it, and then that might have messed you up here. But then down here, what was it asking you to do? Left and right-handed derivatives at that point, which, you know, and this was the delta x crap. So instead of x plus delta x, if it's at a particular point, like -1, instead of plugging in an x in general, you can plug in a -1 plus delta x. But I'm not going to worry about that. We went through enough of that delta x stuff already. Anyway, but this derivative is, if you're on coming in from the left, like x is less than or equal to -1, you're on this graph, x plus 1 quantity squared. The derivative is 2x. So if I plug in, well, I'm on the wrong one. If I plug in -1, you should get -2, right?
So yeah.
Why do I get 0? F prime from the left. Maybe I'm doing that. Am I doing that derivative wrong?
Because it'd be.
Oh, 2 times the quantity x plus 1. I did the derivative wrong. The derivative of this is 2 times the quantity x plus 1 to the first times derivative of what's inside. So if I plug in -1, I get 0 times 2, which is 0. And I think that's what you were doing here. So I actually gave you credit for that, because you were like plugging in -1 to the derivative and getting 0.
Yeah, okay.
I think is what you were doing. And then, like, if I'm approaching -1 from the right, I'm on this line. The derivative of that is 2, right? So if I plug in, I don't know if you're plugging in 0 there, you're supposed to plug in, I think this one you're plugging in -1, because I'm coming to the right side of -1. So the right-hand derivative at -1 is 2. So anywhere on this interval, the derivative is 2. And so for any value of x that you plug in to the derivative, you're going to get an output of 2. So the left-handed derivative at -1 was 0. The right-handed derivative at -1 is the derivative of this one, which is 2, and they're not equal. So if I say, what's the derivative at -1? It doesn't exist, because the left-handed and right-handed derivative aren't equal. And if you look at your picture up here, you have a sharp point, right? So you can't balance a tangent line on that. Coming in from the right here, the tangent line that bounces on there has a slope of 2. Okay, coming in from the left, the slope is changing, but it'd actually be a horizontal tangent line that's on the x-axis coming in from the left, which has a slope of 0. So anyway, the left-handed derivative is 0, right-hand derivative is 2. Therefore, the derivative at -1 doesn't exist, because it's got to be the same from the left and the right, just like a limit. Okay, makes sense?
Okay. Yeah.
Okay, and then you didn't show the left and right-handed derivatives here. Like you just said, they're not the same. You know, you need to prove it. It's true. You could talk about it in general, like if you had a graph, you could actually graph this thing, which I don't know if let me see if I did that. I didn't graph it, but basically it's 1 minus x squared absolute value. Blank whiteboard. I would let you get away with this. So 1 minus x squared, absolute value of that. Well, here's y equals x squared, right? There's minus x squared, and then plus 1 goes up here. So it's actually, here's the graph of 1 minus x squared, right? And if I want the absolute
Yep.
value, what does it do? It takes the positive stays positive and the negative, it'll go like this. It'll make it positive. And so, you know, right there, I don't have a derivative because it's a sharp point, and right there, I don't have a derivative, and that's at the point -1 and +1. So that's the visual way to talk about that. But on my key, I actually calculated the derivative, which is a lot longer of a process with the delta x. All right. Anyway, so let's get away from that. And this is why, you know, chapter 1 was more algebraic stuff. So it was probably easier to follow but this is why I wanted to go through some of this stuff with you. So then moving on past that. Did pretty good. So this one is the theorem. So if I don't say use the definition or use the form, you know, you can use, this is theorem. So this is the way you can normally do it. So same deal here, like number 8 and 14, just put G prime equals that and F prime equals this. You know what I mean?
Gotcha. Yeah.
Okay. I don't know how you're doing these, but like if you got, you know, x to the 5th in the denominator, you can write this as 5, 6, x to the -5th, and then use the power rule. Maybe you're doing that in your head. I don't know.
Yeah. Just
But
I
whatever
did
you're
the
doing,
5, 6.
okay, just show it on your test. I mean, as long as
Okay.
it's right, I don't care, but it'd be good to show it on your test in case it's not right. And here I just kind of put, like, this is h prime at t, so I did that for you here. And I will tell you, like, if you have this and I say no need to simplify, just leave it like the second line here.
Okay. Yeah, I guess
you.
I didn't know, so I just went through and canceled everything out.
No, and that's fine, and it was correct. So, but I'll tell you if I say don't, like the test should tell you if I say don't simplify, just leave it as the second line. Here there was a minus sign out front that actually needed to be, like, it was quantity minus that whole quantity, I believe. So I'm not sure. I don't know. Somehow when you multiplied that out and simplified, you know, it's equivalent. It's almost equivalent to what you wrote, but it was minus x squared plus 4x plus 2 is what you'd get up on top when you do that.
Okay.
This one, not sure
Yeah,
how you
I'm
did
not
it, but
sure.
this would be, yeah, if you do the power rule, 3x to the -1 minus 1/3 x to the -3, it becomes pretty simple to do.
Yeah, I'm not sure why I didn't do that for that one. I think I just overthought that one and try to do
Yeah.
it differently.
Okay, no problem. Everything's easy when you know what you're doing. So I did have yeah, so time you can start at 0, but like doing a chart,
Yeah, I guess we'll have to put
do
a
you,
chart there for.
yeah, do you follow how to do the charts or not?
No, I mean I could like interpret one, but I don't know about putting one together.
Okay, well, you put it together, you break it up with critical numbers. So let's see. It might be better if I just, what section is this? 2.5?
Yeah.
So I'm bringing up keys. So velocity, you know, if right is the positive direction, if the velocity is positive, you're moving right. And if the velocity is
Okay.
negative, you're moving left. If the velocity is 0, you're stopped. That makes sense?
Yeah.
Okay. So we can, Let me, crap. Where'd it go? I'm gonna stop sharing that. I'm gonna share whiteboard. And I gotta clear all that. All right, so what do we have? We have your position is 2t cubed minus 3t squared minus 12t plus 8. That's your position. So you did a good job of saying, like, so you're looking at your homework, right?
Yeah, I have it.
So t equals 0 equals 8 points to the right. Yeah, so at time t equals 0, so position, this is just rectilinear motion. So you're back and forth on this. This is like etch and sketch. So we're just back and forth here. So if this is 0 right here, okay, well, t equals 0. So S is like S evaluated at time t, right? It's a position at time t. So it's really a function of t because you have that here. So what I do is, let's say this is 5, 10. We'll just go by fives here. And you may not want to do this first, but I kind of know, like, so when you have t and then S of t, or just S, if t is 0, S is 8, right? So what I do is I draw this above. So 8 is right here. So this is where we're at when time starts. So t equals 0. And now I'll just label it t equals 0. And if t is 1, like 1 second in, like you had a bunch, you had 5 to the left, so you're at minus 5. And when t is, what did you have? T is 2, 12 to the left, right? So, but the biggest thing is you want to know, like, it's either going right or left from the start. So it looks like between 0 and 1 second, you'd be going left, because at 1, -5, you got to be right here, right?
Yeah.
And I'm drawing this above, but really it's on here and it's back and forth, and that's hard to see. So I mean, basically your particle's moving, right? So you need to know how it's moving. So the velocity does that. So what's the velocity? The velocity is S prime, right? Or ds dt.
Yeah.
And what's that? That's 6t squared minus 6t minus 12, right?
Yep.
Okay. And you're stopped when velocity equals 0, because you're not moving, right?
Yeah,
Okay.
I guess I did there too. With you can't have a negative time either. I guess
Right.
I forgot about that, but I had the t equals 2.
Yep. So you did it. I mean, so you were doing this, and then but you got to set it equal to 0. So yeah. So set that equal to 0. Factor out a 6, and you got t squared minus t minus 2 equals 0. So, factor in that. T minus 2 equals 0. So t equals 2 is all you need, because that one can't have negative time. So anyway, really all I care is about this one. So I'm going to be stopped at 2 seconds. And where am I at? So basically I'm going left. At 2 seconds, I'm going to be at minus 12. So that's t equals 2 seconds, right? And so I got to go from, so basically, because I don't stop anywhere in between, I'm moving that whole time. So from t equals 0, I'm over at 8, and t equals 2, I'm at -12. But I'm going left to that point. Now here's one of two things can happen. I can, like a hitch and go, I can stop and keep going, or I can stop and turn around. So the reality is, I guess you can pick anything you want. Maybe plug in 3 seconds. Where you at? You got 54. I'm going to end up being positive. So what happens is I stop and turn around. And this is your etch and sketch graph. So really what it looks like is I'm here, I go left to -12 at 2 seconds, and then I go back right forever with future time. So it's back and forth on the S axis, but I draw it above. So I'm just like, hey, here we go, boom. Moving left, I stop at 2 seconds, and then I go right. Now, if you put in negative time, that's fine, but we don't want to do that. So all good with that? So that's a velocity when you're stopped. Okay, so the question is, how do you make a chart then? Your only critical number is t equals 2 seconds. That's your critical number. So I'll show you on the velocity chart. Let's see, whiteboard. Okay, so critical numbers, 2 seconds. So basically we got our interval. Come on. So 0 is less than or equal to t is less than 2 seconds. And then we have a test t. So I just pick one in there. So you can pick one. Sine of the velocity. So sine of the velocity. If velocity is positive, you're moving right. If it's negative, you're moving left. And then conclusion for the particle. Okay. So what's the sine of the velocity? Well, what is the velocity? You said the velocity was 6t squared minus 6t minus 12, right? But then we factored that out and said it was 6 times t minus 2 times t plus 1, right?
Mm-hmm.
So really, if I pick 1 and I plug 1 in, I get positive times negative times positive. So it's negative, right?
Correct.
Or you can plug it in here. You could plug 1 in, and it's 6 minus 6, which is 0, minus 12, which is negative 12, which is negative. I don't care what the number is. I just care about the sign of it. So the conclusion is the particle is moving left on this interval. That makes sense?
Yeah.
Okay, and then t equals 2 seconds was a critical number, so we're at 0 or undefined. Of course, the test t here has to be 2, but the sign of the velocity is 0. So what does that mean? It stopped. Particle stopped. All right, and then from bigger than 2, so now everything's going to be the same, not bigger than or equal. Bigger than 2, you could try any number. 3. Well, if I plug that into the velocity here, plug in 3, positive, positive, positive. So basically, multiplying all positive numbers is positive. What does that mean? You're moving right. And then that's what I drew, kind of in that serpentine look, which I am going to want you to graph. So does this make sense on how? So you split up your chart. You start at 0, which you'll remember that now. But then you split it up with critical numbers, and that's where your derivative is 0 or undefined. That's your velocity. So if the velocity is 0, you're stopped. Okay.
Gotcha. So yeah, so you want like 0 and then like where it stopped and then continuing after
split
that.
it up with critical numbers, which is where the velocity is 0. Technically, you could split it up where it's undefined too. Hopefully I don't do that to you. But anyway, when the velocity is 0, you're stopped. Now, I'm just going to change. I'm going to use a different color here. And let's say that this ended up being negative here for the sign of the velocity, which means you're still going left. Well, what did I do? I went left, stopped, and then I kept going left. So it's kind of like a stop and go in the same direction. I didn't turn around.
Yeah.
Right? But in this case, in our case, we went right because I was positive. And so we went right here. So this is a stop and turn around.
Gotcha.
Right? So I was going left and then I stopped and then I'm going right. So really we stopped and turned around. Now you don't have to write that you turned around because it's pretty obvious here. But when you graph it, that helps you. And so instead of just picking, you may not stop until like 12 seconds, right? Depending on the function.
Yeah, I mean, it just depends on where it equals 0.
So you don't want to sit there and like put in, you don't want to plot points t and s of t. You don't want to go 0, 1, 2, 3, etc. to figure out where you're at on the graph if you don't stop until 12 seconds. Really, all I care about is where we start, and when you stopped, where are you, and which direction are you going in between. And there might be 2 stops along the way, right? So if you have 2 critical numbers like 2 and 5, then we're going to split it up 0 to 2, t equals 2, 2 to 5, t equals 5, and then 5 to infinity, or 5 on. T is greater than 5. Make sense?
Yeah.
and then you'll have potentially 2 stops along the way. All right, so that's velocity chart. This is the chart. So when I say make a chart, you know, you showed some work there, came up with critical numbers, you know, so
Yeah.
it doesn't have to look exactly like mine, okay? I'm not gonna just make sure I'm seeing the work and then you're making the conclusion based on that. But basically, the velocity was S prime, right? So you're trying to figure out, are you positive, negative, which way are you going? And I never, like, you just gave me points in time and where you're at, but like I want to see like the serpentine graph. Like, hey, I started here, I'm going left, which you can draw a little arrow like that, and then I stopped here, and now I'm going back to the right. You put arrows,
like,
you know.
Like what you put on the key there at the bottom.
Yes.
Gotcha.
Yep.
Okay.
Okay, and then just real quick one, go back to that. No. Screen, whiteboard, no. I keep hitting the wrong thing and canceling out. But the acceleration is the pull. So I'm gonna I actually do want to share my camera first. So I don't know how, like, were you watching my videos on this stuff or not?
Yeah.
Okay, so which way is that for you?
For me, that's pull.
No, well, yeah, but which way is my hand moving for you?
Oh, for me, to the right. Like your hand's moving to the right.
This is going to your right, like my face, and then it's going to your right.
Yeah.
Okay, that's fine. So that's your velocity. So if velocity is positive, I'm going that way, right?
Yeah.
And then we look at acceleration. Acceleration is the second derivative. Acceleration is like your pull. So think of a rubber band. And you did football drills, right? Did you ever have rubber bands, like a partner holding the rubber band back on you?
Yeah.
So you're running right, but he's pulling the rubber band against you to the left. So the acceleration is a negative when you're going positive direction. The pull was negative. What would happen to you as he pulls? You slow down, right?
Yeah, I wouldn't be able to go as like faster. It wouldn't go.
Right. So basically, when the acceleration is in the opposite direction of the movement, you're slowing down. The particle's slowing down. Does that part make sense?
Yeah. Yeah.
What if you're running to the right and he's in front of you pulling? So the acceleration is pulling you in this positive and pulling you in the same direction. What's going to happen?
Going faster.
You're going to speed up. Think of it as running down a hill. You're going to speed up as you run if you can keep your balance, right? Or if you're riding a bike and you're going downhill, the pull is in the same. The pull is gravitation, or gravity is pull, right? So that's a type of acceleration, but you're going to speed up going downhill. You're going to slow down going uphill. So your movement uphill would be in the positive direction, but gravity's pulling against you. You're going to slow down. If you're going downhill and gravity's pulling you downhill, so your motion, your velocity is positive, and or the same direction as the pull, you're going to speed up. So then the question is, how do you come up with critical numbers for acceleration? Well, acceleration is the second derivative of your position, or it's the derivative of the velocity, right?
Yeah.
So you just take the second derivative. So now I'm going to go back and share my whiteboard, hopefully. I don't know if I can write on it like this or not. Maybe I can, so I might be able to just do this quick. All right, so what did we had? We had the velocity was 6t squared minus 6. I gotta flatten this out again. 6t squared minus 6t minus 12, right?
Yeah.
And we came up with critical numbers. T equals 2 seconds. Velocity was 0, so we were stopped. Okay, well, what about the acceleration? Well, that's v prime. or it's s double prime, the second derivative of your position. That's just 12t minus 6, right?
Yep.
Okay, so critical numbers where the derivative is 0 or undefined, in this case it's the second derivative or it's the derivative of velocity. So where is this 0 or undefined? Set it equal to 0, and we got 12t equals 6. We got t equals 1/2. At 1/2 a second, what is 0? The acceleration equals 0. What does that mean? No pull. So acceleration is like the rubber band. There's no pull at 1/2 second. So I could also do a chart where we have your interval and then your test t and then the sign of the acceleration. So sine of a. So in this case, if I'm only doing acceleration, I only need to split it at 1/2 second. So 0 is less than or equal to t is less than 1/2 second. So whatever t in between there, maybe 1/4. Like if I can write 1/4. Good God, let me write. Okay, and then t equals 1/2 second, and then t is bigger than 1/2 second. Okay, well, at 1/2 second, of course, I know the sine of a is 0 at 1/2 second, right? So the conclusion for my particle, there's no pull. Okay, so what about bigger than 1/2? Well, let's try 1. If I plug in 1 here, 12 minus 6 is 6, which is positive, right?
Yeah, so you're going to the
So
right.
what do I have? I have right pull. So right is my positive direction, right? So I have right pull. If I plug in a 4th here, 12 times a 4th, 12 divided by 4 is 3 minus 6 is negative. So I have negative acceleration here, so that means I have left pull. Make sense?
Yep.
Okay. And then I'm going to show you one more thing about putting it all together. So what were my critical numbers? For velocity, we had t equals 2 was a critical number, right? For acceleration, we had t equals 1/2 was a critical number, right?
Yep.
I could do a chart that splits it up using both of these. So I've got my interval, and I'll go from 0, start at 0 to 1/2, t equals 1/2, and then I can go 1/2 to 2 is less than t is less than 2, t equals 2, and then I can go t is bigger than 2. And then I can have my t that I'm checking out. I can have my sine of my velocity. I could have my sine of my acceleration, and I can have my conclusion for the particle. So I could do this too. So in this case, I'm going to still use a 4th here. I'm going to use a 1/2 here. Easy number in between here is 1. I have to use 2 there, and an easy number bigger than 2 is 3. Okay. Well, we said for the acceleration, less than 1/2 second, it was negative, right? At
Correct.
1/2 second, 0, and bigger than 1/2, the acceleration was positive, right?
Yep.
That's what we just did. So all
Yep.
of these are positive. So what does that mean? So conclusion, just on the acceleration, is no pull here. Left pull there, and then right pull on all of these. All these have right pull. But that's not really what I'm looking for. Let's talk about the velocity. So do you remember what we had for the velocity?
The 6t
It was
squared.
moving left, so it was negative initially, right? Until we got to 2.
Oh, yeah, until we got to 2, because that's the critical number.
So it's going left. So this is still negative here. Come on, let me. Negative, negative until we got to 2, and then it was 0, right? And then it was positive. So I'm going left, 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 stop, and then right, correct? So that was what we had initially. But I'm putting it all together. So now, so the reality is if I'm doing this now, okay, instead of this left pull. Well, I'm going left with left pull. So what does that mean the particle's doing?
It's like going faster to the left, or like there's nothing
Correct.
to
It's
keep it.
speeding up. Yep, so it's speeding up. And then here at 1/2 second, at that moment in time, the particle's moving left, but it's like the rubber band is loose on it and it's not pulling. So that's the moment in time that the pull stops. So we can just say left and no pull. Well, now here from 1/2 second to 2 seconds, I'm still going left, but I've got right pull. So what do you think that means? I'm slowing down.
Yeah, kind of like getting rid of like slingshot to the right, more or less.
Yep. And then I'm stopped, but I still have right pull. So it just gets to the end of that pull. So I still got pull, but my particle can't go left anymore. And then it turns around and goes right. And then at the end, when t is bigger than 2 seconds, I'm right with right pull. So I'm speeding up. So I'm left and slowing down. I'm stopped here with right pull. And then I'm right and speeding up bigger than 2 seconds. Up to 1/2 second, I was going left and speeding up. So anyway, this kind of puts it all together, but that's kind of where you look. All you really need to do is start, where are you starting at time 0, and then get your critical numbers where the velocity and the acceleration are 0. Then you can split your intervals or figure out what's going on. So that might help you because I believe there's one of those on your test.
With it like chart and everything.
Yeah, but you can do, I'm not going to make you do a chart like me, but you have to do the math. So you were doing the math without the chart. So I'll it's independent study. I wasn't like getting back to you very quick on that. So however you do your work on that, that's fine. But I want you to know where the moment in time is that you're able to do that stuff. So or split it up, I mean. So that's just your critical numbers. What is it? I don't understand what this is doing now. You can still hear me?
Yeah, I can hear and see you.
You can see me too? Okay.
Yep.
All right. So let me go back and just finish. I think that was mainly the chapter 2 stuff. Is this helping you at all reviewing for the test or not?
Yeah. Yeah, no, it is.
Okay.
And then, I mean, there's like chapter 2 through 10 or 2.6 through 2.10.
Yep, which I have. Can you see? You can see it here.
Yeah.
So some of these, easiest one, number 22, it says, what's the instantaneous or the marginal cost?
Yeah.
For the 10th one sold, that's C prime at 10, which is correct. So you just plugged in 10 up here on your derivative. That's $3.50. But when it says what's the actual cost of producing the 11th one?
Yeah, I forgot. You take 11 minus 10.
Yeah, total cost. Yeah, so not the derivative. You're not using the derivative function there, but it should be close. So C of 11 minus C of 10 was, I don't know what the actual answer to that was. I think $3.75 or something. It's close to the marginal cost of the 10th one, which is the instantaneous rate of change of cost at that moment. Anyway, they're supposed to be close. So you took the derivative here. I think you're okay on that. Don't, unless you have to, just keep it exact, use pi, so you're fine on that. But this is, you put centimeters for your answer, but it's actually, so dV volume is cubic centimeters and radius is centimeters, so it's actually cubic centimeters per centimeter, which if you were going to label it, you could say square centimeters technically, but I like cubic centimeters per centimeter better as a label. Coming back to number 8, we had the whatever law this is, where pressure times volume is a constant. And I don't have the actual problem, but you want the rate of change of volume compared to pressure. So with that, you gotta solve it for like dB/dP. It's just like, f prime at x is df dx. So if I want v prime, I'm taking the derivative of v with respect to p. So just rewrite, c is just a number, right? It's just a constant. So this is c times p to the -1 power.
C to, okay, yeah.
And then taking the derivative of that would be minus cp to the -2 power, which would be minus c over p squared. So let me
CP, yeah, and then, yeah, so then V would equal negative C P minus 2, or to the negative second power, and then that's just actually V equals negative C over P squared.
This is the wrong. What section is this? Chapter 2. It's
6.
if I do this right, it's fairly quick, but I didn't have it open. So I don't know if you have my keys next to you or not, but
Yeah, I see how you did that. I don't know why. I don't know why I just kept it there, but I see the process of just taking a derivative of the V equals C over P, so then you end up getting V equals negative C over P squared.
yep.
And then you would just plug in the whatever the P equals 4, and then you get the what?
Yeah, and then
16,
you can find, it says when the pressure is 4, the volume is 8, so you can figure out what C is then based on that. And
yeah, because
then,
the 4 times 8, 32, then you substitute 32 over 16, which is, that would be negative 2.
yep.
Yeah.
And
okay.
so this,
Yeah,
it's asking for the rate of change of volume with respect to the pressure. So a rate of change is a derivative. So I always let the words do the talking on. So the rate of change of volume with respect to pressure is dV dP. And then if you had to label it, volume is cubic units and pressure is whatever the label for pressure is in the problem.
There's a bunch of them.
Okay. And so then we got that. Yeah, it was $3.75 there. So, but like on number that 22, that marginal cost or C prime at 10, that was a positive number. And since it's positive, it's a rate of change, right? So this, we could also write this as dC dx. But anyway, so that means the cost is increasing at a rate of DC is $3.50. DX is the number of paperweights, the number of items, right? So if I ended up getting a negative 350, then I would say decreasing at a rate. Yep. Okay. All right, good on that. And then let me go stop sharing that, go back. So really, we probably should be, I know the 4th of July messed with both of us, but I should have went over this stuff with you before you were jumping into chapter 3. I apologize on that, but we'll figure it out. Biggest thing is getting you through it, right?
Yeah, exactly.
All right, and I'm sure.
7. Oh, do 2.7. Okay, perfect.
So 2.7, yeah, this was 2.7 and 2.8. You did really well on. Check marks are good. You know that, right? I don't know if I told you that.
Yeah.
Anyway, so you're using quotient rule here, things like that. This is, you do the derivative and then plug in, you're fine. Chain rule, we have some chain rule stuff. So anyway, sine of x squared, you act like it's okay. So derivative of sine is cosine of that thing times the derivative of what's inside. Derivative of x squared is 2x. So you're fine. But yeah, just that these aren't equal to each other. This is g.
Yeah,
This is
that's where.
yeah.
Gotcha.
Which yeah, and trust me, I know what you meant. I'm just putting that there for you. So, and then let's see down here. So this is tangent squared of x squared. And then we have the next one, but this is easier to me to write it as tangent of x squared quantity squared. So I don't know if I have, is this 2.9 or 2.8?
This is 2.8.
Do you have my key, or do you?
Yeah, I'm pulling it up now.
Actually, this one would probably be better. I'll just do these real quick so you can hear me talk through it. You can look at my key so you don't have to write anything down because you got my key. All right, try and flip that around again. Okay, so we had, stop it. Tangent squared of x squared, and you want the derivative of that, right?
Correct.
Like y, you want y prime. Okay, so I'm going to rewrite this as tangent of x squared quantity squared. And then how do you do it? It's something to a power. So I'm going to use the generalized power rule. So I'm going to take that, drop it down in front. And then that thing to the first. But then I got to use a chain rule and take it times the derivative of what's inside. So it's 2 tangent of x squared to the first power, right? Because you reduce it by 1.
Yep.
But then I got to take it times the derivative of what's inside by the chain rule. Well, this is tangent of a function. So the derivative of tangent is secant squared, right?
Yep.
But it's secant squared of this thing, which is x squared, right? And then because that's not just an x, I also have to use a chain rule and take it times the derivative of what's inside of this, which is x squared. So that'd be times 2x. So I got to use a chain rule twice. So I had to use a chain rule. First of all, I rewrote it so I could think of this as, a function to a power to use the power rule. So 2, that thing to the first, times derivative of what's inside by the chain rule. So that's the green derivative of tangent secant squared of that thing. But that's not an x, so I got to use a chain rule again. And the derivative of x squared is 2x. And then I simplify. And so it ends up being y prime is going to be equivalent to, I got 2 times 2 is 4x. So there's my x. So that's 4x tangent x squared secant squared x squared for the final answer.
Gotcha. Okay. Yeah, that makes it a little bit easier.
Okay. Dang it. I didn't mean to. And then I'm going to do the next one real quick. Mm-hmm.
Yeah. So I guess, it's like that power rule where you just keep taking the derivative of the derivative of the derivative for like what's inside of the.
If it's not just an x, you got to use a chain rule. If it's a function and not just an x, you got to use a chain rule. Take the derivative of what's inside. Easiest way to think about it. And then I'm going to just step you through how I think of the, get the next one here, just a second. Sine squared cosine 2x.
Yep.
So I just think of this as sine squared of something. Oh my God, this thing. All right, so I'm going to rewrite this as sine of that thing, like that could be a z, right? Anyway, quantity squared. And then, so this is y, then y prime, I'm going to use the power rule first. So it's 2 that thing. Oh my God, what is going on? I told you I get technical difficulties all the time. Come on, let me draw. Actually, let me erase. I have no idea where that came from. All right, 2 that thing sine of cosine 2x to the first, right? Which
Yeah.
I don't need to put that. But then times the derivative of what's inside, because that was a function, right?
So, yep, so it's cosine.
So derivative of that by the chain rule, derivative of sine is cosine of that thing. So like if cosine of 2x was a z, it'd be times, so it's sine of z. Derivative of that is cosine of z. But it's not a z, it's cosine of cosine 2x. So that's fine, but I got to take the derivative of what's inside there, right? By the chain
Yep.
rule. So the derivative of cosine is minus the sine, right?
Yep.
Of 2x, if it lets me draw.
And then take that times the derivative of.
And then because that's not just a x, I got to take it times the derivative of the 2x, so it's going to be times 2. Make sense?
Yep. And then you just simplify that all together then.
Yeah, and then you set, so yeah, then times 2. And so it ends up being equivalent to just kind of minus sign 2, 2 is 4, so it's minus 4. And then I'll use this one next, sine of 2x. So that's that one, the minus, that's gone. And then sine of cosine 2x times cosine of cosine 2x. Okay, all good?
Yeah.
I kind of buzzed through that, but time to move on. So, what? Oh, yeah. All right. Get back. I think, let's see. You thought I was kidding when I said plan on an hour with me. All right, this one.
Yeah, 2/9.
So, and you might, instead of me, like, these are chain rules as well, but the reality is I'm going to take number 14, I'm going to write that as a quotient, like that fraction in there, to the 1/2 power.
Yeah, okay.
And I don't know if my key says that. I'm not looking at my keys right now, but
So you said
that'd
from
be,
14? Yeah, that's what you do on your key.
okay. I mean, so you just basically, some of this stuff, you just got to use algebra tricks. I would probably say don't simplify on the test, but obviously on homework, I would want you to simplify. The other way is take it, the top one to the 1/2 power divided by the bottom one to the 1/2 power is another algebraic manipulation, use quotient rule. But you got to, then you got to use the power rule and the chain rule within the quotient rule.
Yeah, so I mean, like, it's like on the test for like 14, like where, like, can we just like go through to like where I would not have to like keep simplifying?
Yep. Do you want me to?
You can just do 14
my
and
white.
just use that one as an example.
Okay. Yep. I gotta get back to the screen. All right. So, your blank whiteboard. So basically, I'm going to rewrite that as cosine x minus 1 over sine x. I'm going to write that quantity to the 1/2 power. So that's whatever y equals that, or I want the derivative of that. So y prime 1/2 that thing to the minus 1/2. So that'd be cosine x minus 1 all over sine x. So that interior part didn't change. But then times the derivative of what's inside. And, I don't care if you use, but this, whoa. No, how that's going. But anyway, so I got to use a quotient rule here, right?
Yeah.
I don't want a box. Where, like, good Lord. Okay. I don't know why. Anyway, so it's bottom times derivative of the top. Derivative of cosine is minus the sine. And then minus the top, cosine x minus 1 times the derivative of the bottom. Derivative of the bottom is cosine x all over the bottom 1 squared. So it'd be sine squared x. So probably on a test, if I say don't simplify, you can just stop right here.
Okay. Just make
Okay.
sure you're getting to, yeah, to use that
But you
rule.
got to show the chain rule part, right? And everything. But yeah,
So
you'd
it'd
be able
equal
to
to
stop
sine.
there.
Okay.
All right. So
Instead of trying to go through and simplify the rest of that stuff out then.
that, yeah, and that, you know, I spend like 15 minutes in class showing different ways to simplify it. So there's, but that's just algebra monotony. So let me get back to, oh, whiteboard. I just went out of that so I can maybe get back to normal. And then, okay, so I think I'm good now. I'm just going to show you then that next one, we had like cotangent of xy plus xy equals 0. Now you have taken the derivative. You're trying to find dy dx, right? That's what we want. We want dy dx. But the thing is, y is a function of x. So anytime you have a y in there and you're taking a derivative, you got to attach a dy dx by the chain rule. So really what you're doing is taking both sides of this, taking the derivative with respect to x of both sides, right?
Yeah.
Okay. So in this case, on the, you know, derivative of cotangent, derivative of tangent secant squared. So it's minus cosecant squared of xy, right? But then times the derivative of what's inside, correct? So I got to
Yep.
take it times the derivative of x times y. Well, guess what? I got to use product rule. So it's first times the derivative of the second, derivative of y. You act like it's okay, so that'd be 1. But then because it was a y, I attach a dy dx. Plus the second, which is y times the derivative of the first one with respect to x. So the derivative of x with respect to x is 1. So y times 1 or just y. So that's just the derivative of this first part. And then plus the derivative of the second part with respect to x. You know, that I got to use product rule again, right? So it's first times the derivative of the second. The derivative of y with respect to x is just dy dx, or 1 dy dx, right?
Yeah.
Plus the second one times the derivative of the first one is y times 1. And then on the right, I don't care if this would have been a 100 over here. On the right, the derivative of any constant with respect to x with respect to any variable is 0, right? Derivative of constant is 0, right?
Yeah.
But it was a 0, I think, already, so it didn't matter. And then what do we do now? Now we got to get all the terms that are dy dx's on one side, everything else on the other. So I'm going to multiply this through just the distributive law. And I have, so just the first one here, it's minus x. So if I put that first, cosecant squared xy dy dx. And then I've got that one I'm going to put on the other side. So minus y cosecant squared xy, I'm going to put on the other side as a positive. Cosecant squared xy. And the reason I did that is there's no dy dx term there. And then I have plus x dy dx. So I'm getting all my dy dx terms to the left, everything else to the right. So then this would be a plus y I want on the other side, so that's minus y, right? if I can fit it on there. And so instead of having the equals 0, I have equals this stuff in black. You following me or not? Or did I lose you?
No, I'm just, yeah, okay, I see. I didn't see that I just trying, yeah, okay, I just forgot that last term with a Y to move it over. Okay. Yeah, because we're,
Yeah,
okay.
so going forward, like when you're in chapter 4, like you were apparently stuck on number 30, like you just reach out to me, dude, right? Like we can get on this and I can step you through it. So I don't want you sitting there having no idea how to do a problem.
Okay.
So like, but anyway, so on this, basically you're taking the derivative, but you got y as a function of x, right? So y could be like cubed root of cosine x. You don't know what it is, so but it's a function of x. So when you have a y in there and you take the derivative, you got to attach a dy dx by the chain rule. So this is called implicit differentiation, but it's really just a chain rule. And then when I multiplied this out, like the second term did not have a dy dx. So I want to get everything on the right side that doesn't have a dy dx, and everything on the left side keep the dy dx. And the reason I do that is because if I have a color that I haven't used, gray, I can factor out a dy dx from both terms, and I've got dy dx, and then what's left is minus x cosecant squared xy plus x, right?
Yeah.
Instead of this. And then now to solve for dy dx, I can divide both sides by that. So I'll end up with the minus x cosecant squared xy plus x. And then that simplifies a little bit more on my key because I can factor a y out on top and I can factor out an x out on the bottom and get some nice cancellation going. Okay.
Yeah, so I mean all that just to get the opposite of y over x.
Yeah, because the cosecant squared of xy minus 1 would cancel.
Gotcha.
If I factor out a y on top, so like, it's a binomial on top. So I just factor out a y. And on the bottom, I can factor out a minus x, I guess. And,
gotcha.
and the
Okay.
You're looking at the key, right?
Yeah, yep.
Okay, perfect. I have no idea what time it is. 4 o'clock? Okay. Yeah. And Amber would be flexible, so if you like need to eat or something when we're done or look stuff over a little bit more, she'll be flexible. I know I talked to her yesterday and today, so. Okay. But I just want to make sure that I go through enough that you know, at least aware of what I'm trying to have you do there. Let's see. Whiteboard.
Yeah, what expecting?
Want to look at 210 quick?
Yeah.
We can look at number 2. I don't know what you did.
Yeah. Well, let me see if I have your key for 210. Okay, 210. Yeah, okay, excellent. So we're just
Okay. And then, so this is the problem. X over y equals 10, and then it says dx dt equals -5, and it wants to know what dy dt is. Okay. All right. So here's the thing. This is implicit differentiation again, but we're taking the derivative with respect to what? With respect to t. So really, x is like x of t, and y is a function of t as well. So y is like y of t, kind of like that position function s. When we have velocity and acceleration, s is really s of t, v is really velocity in terms of time, v of t, and a, the acceleration, is really a of t, right?
Yeah.
So similar deal here. So really what we're doing is we're taking the derivative of both sides with respect to t. So there's a couple different ways to do it. I use the quotient rule on my key, but I'm going to make this a lot easier for you. I'm not going to use the quotient rule. I'm going to rewrite this as x equals 10y. So if I did that and move that y up,
Yeah.
I can do that, right? Now, if I take the derivative of both sides with respect to t, what would I get? I'd get dx dt equals what? Well, the derivative of this, you act like it's okay, it's a variable, so the derivative of 10y is 10, but it was a y, not a t, right? So I attach a dy dt by implicit differentiation. Okay? Make sense?
Gotcha. Yeah.
I need to change my key because this is so much easier. So anyway, -5 is dx dt, so I'm going to plug that in right here. And so I got -5 equals 10 dy dt. And you're trying to find dy dt, divide both sides by 10, and you get -1/2. Isn't that a lot easier than using the stupid ass quotient rule that I used?
Yeah. Seems much.
So that was an algebraic manipulation. I need to write that down. What number is that? Number 2. Section 210. Yeah. Anyway, so that's it. That's all I was looking for. But once again, I'm taking the derivative with respect to t. So when you just act like it's okay, but then attach, if it was a y, attach a dy dt since you took it with respect to t. If it was an x, I mean, the derivative of x is 1, right? But then I got to attach a dx dt. So if you were wondering where that came from. So you can act like it's okay. So 1, x to the 0, or, derivative of x with respect to x is 1. But the other way you can say it is, hey, what's the derivative of x with respect to t? Well, it's just dx dt is the other way to think about that. Okay. Probably good on that. And let's move on to chapter 3. Any you good on that?
Yeah. Yeah. No, that makes it a lot simpler.
Okay. So for chapter
I lost you. I can't hear you.
Are you there?
Yep, I can hear you.
Sorry, man. I hit the closeout button. Maybe.
Oh, there you go.
Yeah, my bad. All right. All right, and then I have no idea. It looks like it's still recording too, but it's fine.
Yeah, I mean, it still has like a little like record thing on the top left.
Okay. So it recorded quite. So if you said anything bad about me, I'm gonna know it, dude.
Yeah, go back there and listen.
Yeah, probably not. But anyway, all right, and then application. Let's go to your chapter 3 homework. All right. How much did you get to look over at this already?
For chapter 3.
Yeah.
I looked at like the first 2, like one, or the first one, so like 1.1 to 1.3.
Okay. So when you have, relative extrema relative max or relative min can occur when the derivative is 0 or undefined, right? Those are critical
Yep.
numbers. But then when you have a closed interval, you also have to check the endpoints for absolute, which is the highest high and the lowest low is the absolute max and the absolute min. And this is just more of a, you didn't miss any points on this one, but like the max doesn't equal -5, 0. That's where it occurs. That's the ordered pair. So like, not that one, but like this point right here on number 2, that's a relative maximum, right? So if that's I don't know what the height is there, but if that's a height of 16, then that's what the relative maximum is. So anyway, the height, the output, the absolute max is the height, and the absolute minimum is absolute minimum height. So it's just where it occurs versus what it is. So okay. I just want to make sure you're square on that. And you just answer the question. If it says, what is the absolute minimum value? That means the absolute minimum height value. So the answer for number 44 would be -7, sorry. If it says, where does it occur? Okay. It occurs when X, or in this case, R equals 2. It occurs at the right endpoint for this interval. So just so you're aware of that. Here, it just basically, you're not including the endpoints, so you gotta be careful. So we get closer and closer and closer to a height of 0 from the top side, but you never hit 0. If this was a closed interval, then your minimum height, absolute minimum, would be 0. Okay.
Okay. So yeah. So there's no minimum there. There's just a maximum.
Right, because those are open dots. You're not actually hitting those endpoints. Because it's not a bracket here. It's open interval, not including -2. So like I could be at -1.99999 and plug that in up here, but I can't plug in -2 because I'm not including it. Okay.
Gotcha.
Yeah, kind of same deal here. So where it occurs is at -1, and what it is, you know, when you plug it in, you get -2 for the absolute minimum height.
Yeah, and I guess like when I was like watching like the videos for 3.2 or whatever, I remember you saying something about. I remember you like saying something about like how it's kind of tricky of like how you word it or whatever. So like -2 is like the value, but like it occurs at like X equals 0.
So absolute and relative extrema are the heights that you hit. So they're heights. So it's the output. And I mean, that's what you're trying to show here. You just -1 doesn't equal -2. So that, you know, I didn't take off for this. I'm just letting you know that, and then just answer my question. So if I say, what's the absolute minimum, you're going to give me -2 for the answer. But if I say, you know, where does it occur, or, you know, how many rackets are produced for maximum profit. If X is the number of rackets, of course you can't have negative number here, but you know what I mean? So just answer your question on that.
Gotcha.
Here you were fine. This is approximate. Keep it exact if you can, but then the question on 24B was, what are the dimensions? You only gave the height, but you need to go back. If you have the height, you can use that original formula that you had up here or something and give me the radius. So you didn't do that.
Gotcha. Okay.
And then here we're using, so when we're using Rolle's theorem or the mean value theorem, so we're starting out and you're saying, first of all, I got to show continuity on the closed interval, differentiability on the open interval, and then whatever happens, right? So you said it's continuous, but you got to tell me why. Easy if it's a polynomial. Yeah, just put poly. Okay. And then differentiable, like you took the derivative, so just go ahead and write f prime equals that. You can do that if you want. You could also say it's a poly. So polynomials are continuous and differentiable on all real numbers. But if it was like a fractional thing or something like that, you might actually need to tell me what it is. Anyway, and then, so then there exists some point in the open interval strictly in between 1 and 2 such that f prime at c equals 0. Well, this is f prime at x right here, right? So what's f prime at c?
Yeah.
Yeah, so what's f prime at c? You just plug a c in instead of a x. So 3x squared minus 4c minus 1, or 3c squared, but equals 0, right? So
correct.
And the question is, where does this equal 0? So you didn't really answer that. You just plugged in a 1 and acted like that was 0.
Gotcha. Okay, so then for that.
3, yeah, and so you're kind of guessing at the answer, but 3, if you plug in 1, 3 minus 4 is -1, minus 1 is -2, not 0. So anyway, you got to, in this case, you can do -b plus or minus square root of b squared minus 4ac all over 2a, right? Which is on my sheet, on my grade sheet. Okay, same deal here. Now we're using, I think this is the mean value theorem. So continuous on the closed interval, you can just say it's a polynomial. Differentiable on the open interval, you can also say it's a polynomial. You took the derivative, which is fine. Then there exists some number in, should be strictly in between, I believe. So that's open interval, such that what f of b minus f of a all over b minus a equals -3.
Equals,
so when you get this, so I mean, you did good work. You did a lot of good work here, but when you get here and you got 3c squared plus 2c minus 1 equals 3, and you're like, well, what value does that? Get everything to one, so when it's a quadratic, get everything to one side and set it equal to 0. So add 3 to both sides, which you did. But if you can't factor this, use a quadratic formula.
Gotcha.
Like the -b plus or minus square root of b squared minus 4ac all over 2a to come up with the two options. Okay. And then, so a couple of things. So similar to the velocity is the first derivative, right, of position back in chapter 2. And when the velocity is positive, if right is the positive direction, you're moving right, correct? Well, when we're using graphing stuff, when you take the derivative, you can find critical numbers. And here, if you set the derivative equal to 0, where it equals 0 or is undefined, those are critical numbers. So here, just set it equal to 0, and -1 when you plug that in is 0, or 3 when you plug that in is 0, right? So you had a positive one, but then
should have been negative.
Yes, but you didn't tell me what the output is. right? Like, I mean, so if you plug in f of 3, 3 is a critical number. It's a potential relative extrema, relative max or relative min. Just plug it in, and you get negative 27. So at 3, you're down here. That's a, whoa, who wrote relative max on that?
Should be
Oh,
boy.
right. So it's actually relative min. So I put in what you said. You said, hey, this is the max. No, it's a relative min, right?
Gotcha. Okay. Yeah. Okay. Well, yeah, that
But
probably messed it up when I plugged in like a positive one instead of a negative one then too.
right. But and then so where you're increasing or decreasing, you got to be, you're increasing when the derivative is positive, and you're decreasing when the derivative is negative. Now, if you know what the graph looks like, which you did on this case, and I don't know if you use a graphing calculator or not, but you can on a test, you can use the intervals, like break it up like we did for the velocity. The sign of the first derivative. If the sign of the first derivative is positive, my function is increasing. So you would split up between negative infinity and negative 1, and then x equals negative 1, and then negative 1 to 3, x equals 3, and then 3 to infinity. But if your graph goes from increasing to decreasing, you have a relative max. So these are wrong. I mean, it's not a min, so make sure you cross that out. It's actually a max. I was just showing you here. But anyway, and then if you go from decreasing to increasing, it's a relative minimum. And so, we went from, at negative 1, we went from increasing to decreasing. Increasing to decreasing, so it's going to be a relative max. So you got these parts right here. Like you had that right on the intervals. And you split it up. All you got to do is check intervals that are split up by your critical numbers, which you got right here. And I understand that's just a minor mistake. So I might have took off. I might have been a little hard on grading this problem, but you didn't give me the x-intercepts. That's where your height is 0. So set your function equal to 0 and factor first, so I could pull out an x, and then you could give me all 3 of these. It actually crosses the origin. And anyway, so I probably should only took off 1.5. I'll give you an extra half point at the end. And then number 40, I wanted to show you this. This is the derivative graph, not f.
Oh, okay.
So what does that mean? So you're answering questions for f of x, not the derivative. The derivative is in, like, if you're can you see my little white thing moving?
Yeah.
So yeah, from 0 to whatever point this is, your derivative graph is increasing, and your derivative graph has a relative max there, but that's not what it's asking you. It's asking where is f increasing or decreasing, and where does f have a relative max or relative min? So then we go back to, if your derivative is positive, what do you know about your function? If your derivative is positive, it's increasing. So how do you know if the derivative is positive? In this case, if it's above the x-axis, it's positive. So from -4 to -2, my derivative is positive, right?
Yeah.
So from -4 to -2, my function f is increasing because f prime is positive. And then also this hump, which is above the x-axis, from 0 to whatever, 3, I guess is where that is. From 0 to 3, I'm above the x-axis, which means f prime is positive. So I'm also f is increasing there. Does that make sense?
Yeah. So okay. So what I answered it was supposed to be questions for f of x, not f prime, right?
Not f prime. Yep. They gave you the derivative graph to answer questions about your original function f.
Gotcha. Okay.
And then, so where is f decreasing? Well, when the derivative is less than 0 or where the derivative is negative, so that'd be below the x-axis. So down, so negative infinity to negative 4, negative 2 to 0, it's below the x-axis, and from 3 out. So those 3 intervals, f would be decreasing. Now I'm going to mention one more thing too. So where do potential relative extrema, relative max, relative mins occur? When your derivative is 0 or undefined, right? Those are your critical numbers and possible relative extrema. So when you say where's a possible relative max or relative min, the only options, because this f prime is not undefined anywhere, it's defined everywhere, right?
Yep.
So the only options for possible relative max or relative min is when x equals -4, when x equals -2, when x equals 0, or when x equals 3. Does that make sense?
Yeah.
And then you can figure it out. So if it goes from increasing to decreasing, which I kind of go like it's a hump, increasing to decreasing, it's a relative max. So where did I do that? At -2, like -4 to -2, I'm increasing. And from -2 to 0, I'm decreasing. So at -2, I went from increasing to decreasing. So at x equals
so that'd be the
-2, I
max.
have a relative max.
Gotcha. Okay.
Did I do that wrong? I went from.
I mean, what you just said, it made sense.
I went from increasing to decreasing as a relative max. I think I switched these. I think I switched those around. I said it right, but I didn't write it right up here.
Okay. I'll just pay attention to what you're saying then.
Yeah, well, check my key. But on this, you might just draw a double arrow here on yours, but okay, getting low on battery, but I'll plug in if I have to. We're almost done here. And then concavity. So I asked for a chart, but concavity is like acceleration. It's the second derivative. And so once again, where do you split it up? Where the derivative is 0 or undefined. So in this case, you take the second derivative and x equals 0 and x equals 1 are your 2 points. And if you switch concavity, that's an inflection point. But the sign of your second derivative, if the sign of the second derivative is positive on an interval, you're concave up. And if it's negative, you're concave down. So that's like the acceleration. When the acceleration, which is the second derivative of position, when that was positive, you had right pull. When it was negative, you had left pull. Similar here. So this section 3.5 is similar to that as well. So all your answers were right. I think I asked for a chart. So you just, whether you do it or just give me the math, like this is f prime and this is f double prime, and then you set it equal to 0. Basically, you got critical numbers here. I knew what you were doing, but just kind of spell out the math, right? F prime equals F double prime equals, and then stuff like that. So I don't know if I say it, like, I think I tell you to give me a chart on the velocity and acceleration one, but just make sure you're writing out what you're coming up with. So anyway,
I'll say, I guess on 12 I did the prime and double prime, but I just didn't.
And that's fine. So you're just getting the critical numbers for concavity. But if I wanted critical numbers, like if I wanted to put a whole thing together, which I think you do have to do on the test, is graph something, you're going to want critical numbers for the derivative. So you can figure out, so like at x equals -2, that's also a critical number for increasing and decreasing. Because if f prime is positive, it's f is increasing, and if it's negative, f is decreasing. So you want that, and then you also get critical numbers from the second derivative. So when I say chart, it's like when I did the velocity and acceleration together, you could do critical numbers for f prime and f double prime together. F prime is split up and it talks about increasing, decreasing. and F double prime is split up and it talks about concave up or concave down. But anyway, it would help you graph it if you have to graph it.
Okay, for the concavity or concavity.
Concavity helps you graph it, yes. So I think I have a video in section 3.5 or 3.4 and 3.5 where I graph a function using the critical numbers based on F prime for increasing, decreasing, and F double prime for concavity. And so I'm sure that I'm going to have you graph a function and show like where it's increasing, where it's decreasing, where it's concave up, where it's concave down, where the relative max, relative mins are, and where the inflection points are. So you got to kind of put it all together to come up with a graph.
Okay. I'll see if I can watch that. You said it's 3.3.5, I think.
Yeah, somewhere in there. I can. This is the keys. Let's see. Chapter. I should be able to tell you. I'm looking at. You probably can't see what I'm looking at, but I'm looking at the videos. 3.5 videos. Graphing example using all critical points. It's in section 3.5. It's the third to the last one.
Okay.
Yeah.
Watch that.
Well, excuse me, for you, second to last one because one's hidden, but it's graphing example using all critical points. And I do a chart, but you don't have, you can do your own methods. You got to come up with the critical numbers. First derivative critical numbers is going to tell you where the function is increasing or decreasing. Second derivative critical numbers tells you where it's concave up or concave down. And then you can come up with your conclusions.
Okay.
But it's, yeah, graphing example using all critical points. I'd watch that. You don't have to do the chart like I do, but you gotta come up with those values doing the math, doing the calculus.
For the graph.
Yeah, and then you'll have to graph it. Like you have to graph a picture of it.
Okay.
So. All right, so I think it's a lot to throw at you. I don't know what else you got going tonight, but like I say, I mean, we can, I don't know when Amber's leaving. What time, like, do you want, or, I mean, how much more time do you want? Or do you want to just watch that video and go take it?
Yeah, I was gonna say I might just see if I text real quick and say if like 5:30 would work just to watch that one video. So that'd be the only thing I'd really do, and just like I just go over everything like one more time probably and just watch that video, and that's probably all I'd do.
Okay. Sounds good, man. Well, I'll let you go. So I apologize for not taking time with you before this, but I know you're working hard at this stuff. There was enough stuff that I was seeing that I wanted to go through and kind of talk you through it.
Yeah, just go over and clear stuff up too. That kind of helped just to make sure that like I felt like I actually knew what I was doing too, that I wasn't, doing stuff wrong either. So.
Yep. You bet. So then we'll, and then there may be one or two, just show as much work as you can. And then we'll go from there. So, if you're not sure what to do, just do as much as you can. And then, we can go through that. We can go through the first test before, before you take your final, but chapter 4 stuff. And when do you want the grade by? Like, when you got to let them know? End of July?
Yeah.
Okay.
Yeah.
Right.
Well, I mean, if they know I'm enrolled anyway, then it can be delayed. But like they said, just if it's by a couple of days, that's fine. Just to let them know. But just by the end of July would be the deadline.
Okay. Yeah, we might let them know because technically they enrolled you in the 10-week
Yeah.
summer, which for an official grade comes out later. But I guess Amber's gonna be on vacation with me. We got to be August 1st. I got football camp, so I got to be back in Carroll by July 31st. But we're gonna have to figure something out on, get through this and then we'll
Yeah.
and get going. I opened up chapter 4. You don't have to do the last 2 sections, but you got to do the
Okay.
first 8. So you can,
So
you know,
so it'll be chapter 4. You said it's the last one, correct?
yes.
Okay.
So 8 out of the 10
Uh,
sections that the homework I opened up where you can see the homework on there. So
Okay.
anyway, just you can take the rest of the night off, but then you'll want to get after it a little bit,
This week.
fairly
Yeah, for
soon
sure.
this week so we can finish up.
So will that be a chapter 4 test and a final, or is that just a final?
Nope, it'll be combined.
Okay.
So
Gotcha.
we'll
Okay. Just want to make sure that
it'll be, so you only have one more test after this, but it'll probably be 200 points.
Okay.
So it'll be like half and half,
Okay.
half comprehensive, half chapter 4.
Okay. I gotcha. Just like the highlights of the first 3, and then like a whole chapter
Yep.
4 test, basically. Okay.
Exactly. You bet. All right. Well, yeah, text Amber and do what's best. Good luck, and I'll talk to you soon.
Yeah, perfect. No, thank you so much for this today. And then I just texted Amber, so hopefully we'll just get that done like about 5:30 or so, and I'll talk to you later this week or something.
Okay. Sounds good. See you, Soren.
Yep. Thank you.
You bet. Bye.